No introduction today. We're just jumping right into solubility.
We're live.
Yes, we are live. Action. All right, so basically I'm going to take solubility and I'm going to talk to you about it in depth. But. What's so funny?
You always look different when you're recording.
Do I?
Yes.
Not really. What you guys need to understand is a simple concept. Like dissolves like. Say it.
Like dissolves like.
Say it one more time.
Like dissolves like.
Dissolve light.
Yeah. Okay. So, have any of you ever tried to mix oil and water before?
Yes, Porter.
Do they mix?
No.
No. So, what you guys are observing is water, which is polar or nonpolar? Very polar. And you're trying to mix into it a nonpolar substance. Like dissolves like would indicate that the oil, because it's nonpolar, would not mix with the polar water. Polar dissolves polar. Nonpolar dissolves nonpolar. Polar and nonpolar do not mix. That's what like dissolves like means. But when we get down into the nitty-gritty, you can actually look specifically at the IMFs that are broken and reformed when you're mixing substances together as evidence of this concept like dissolves like. So, take a look at this example. Hexane. What do you know about hexane?
Nothing whatsoever.
Yes, you do. Hex. What does that mean? Six. Six what? Well, 6 carbons. 1, 2, 3, 4, 5, 6. Everywhere that I have a line going to something that's not written in, it's implied that it's a carbon. So I have 6 carbons in that chain. What about pentane? What do you think that is? 5. 1, 2, 3, 4, 5. Add my hydrogens in. There is pentane. Now, are these two substances polar or nonpolar? They're both nonpolar. So what type of IMFs exist in a sample of them? London dispersion forces. Very good. So, if I'm going to mix them together, that literally means I'm going to have to break all of these London dispersion forces in the samples of hexane and pentane. Because ultimately, I want them to mix together. So, here's the concept you really need to understand. And this will come back later too when we talk about energy that goes into breaking bonds. But whenever you're trying to overcome an intermolecular force, it's going to require a certain amount of energy. Picture 2 magnets. You have 2 magnets together. How do you get them apart? You pull them. When you pull, that requires energy. Would you agree? Now, here's the concept that you probably really haven't thought too much about. What happens when you put 2 magnets together? Yeah, they attract, but are you putting any energy into putting the magnets together? No, not really, but the opposite is happening. We are actually releasing energy when those two come together. So whenever you put energy into breaking an intermolecular force, whenever you put 2 substances together that reform that intermolecular force, energy is going to be released. The concept here is simple. In order to mix one substance with another, you have to have a net change in energy of 0. So if you're going to go and break a bunch of London dispersion forces, you need to reform all those London dispersion forces. So a net change of 0. Now, look down here. Pentane does not dissolve in water. Why? Like dissolves like. Nonpolar will not dissolve in polar. What type of IMFs are you having to break with your water molecules? Hydrogen bonds. Now, if I break those hydrogen bonds, but then replace them with London dispersion forces, we're breaking a high energy IMF and only replacing it with a low energy IMF. So I'm only releasing a low amount of energy while requiring a high amount of energy to break those IMFs. Does that make sense? The net change is not going to be zero at that point. It takes more energy to break your water apart than what you're going to give back with reforming all the London dispersion forces between pentane and water. All right, so again, stepping away from covalent compounds and back into ionic. We know about substances dissolving in water. One classic example that you guys all have experience with is NaCl, table salt. Has anybody ever dissolved that in water before? If you haven't, when you're boiling water for pasta, add some salt in. It makes it really tasty. When you're boiling water for pasta, add some salt into the water. It makes it really tasty. Yeah. Yeah, seriously.
I don't cook.
No, you always have to season your water to make your pasta tasty. What? I don't know. Okay. So, anyways, what exactly is happening here? NaCl is starting out as a solid. When it dissolves into water, what does it look like? What does aqueous mean? Remember back to our unit on matter. Aqueous literally means it is a homogeneous mixture with water. Can you see your substance mixed into the water? No. It appears transparent. Hey, get off Snapchat. So, yeah, I did call you on the thing. Just to prove that I talk normal when I'm making a recording. So, when NaCl, hey, listen, when NaCl dissolves into water, it dissociates into Na plus, aqueous, and Cl minus, aqueous. Dissociates means it literally is breaking apart into its component ions. So instead of picturing NaCl floating around your water, you need to picture Na plus and Cl minuses floating around your water. Okay? So when it's fully mixed in with water, it's Na plus and Cl minus all floating around. Now, what does dissolving, what does solubility really mean when it comes to making mixtures with water? This is the same whether you have a covalent compound that's soluble in water or whether you have an ionic compound that's soluble in water. Basically, what you need to picture is that your water molecules are completely surrounding each ion, if it's ionic, or each individual molecule, if it's covalent. So take, for instance, your Na+. Na plus is floating all around. But in order for that to happen, it has to be completely surrounded by H2O. Now, why am I drawing my waters this way? Very good. If you consider the polarity, your oxygen has a negative pole, making it attracted to your Na+. Now, what about the Cl minus? Cl minus, what's going to be attracted to the Cl minus? your positive pole, which is what? Your hydrogens. So, my water is going to be facing the Cl minus this way. And your negative pole, or your negative ion of chlorine, is going to be attracted to the positive poles of your hydrogens. So your water molecules are completely surrounding the substances that they are dissolving. That's what it means for something to be soluble in water. Questions?